believe it or not. We have almost all of it for 2 dimensions. So this is the formula we're now going to use. So here's what I'd like to do. X squared plus y squared equals r squared. I want you to find their circumference. Well, I already know the formula. Great, prove it. I'm asking you to prove the formula. Everything geometrically in our lives we accepted blindly. Yeah, and probably it was the truth. But then in Calc 1, when you started doing volumes by rotations, you remember doing that? And then you found maybe the volume of a sphere by rotating a semicircle. You know, oh my gosh, it took literally the end of Calc 1, I finally knew the volume of a sphere. Or then you took a couple line, took a line segment, rotated it, found the volume of a circular cone, things like that. You needed calculus in order to do this. It's not possible to do it without calculus. Do you guys remember doing that in your Calc 1 class? You say, oh my goodness, I've accepted these formulas my whole life and I didn't realize they can be derived, but they needed calculus. Which always to me begs the question. The ancient Greeks knew these formulas. 4th century BC. Calculus was invented in the 18th century. The start of calculus. Most of it was 19th and 20th. How did the ancient Greeks know these 2,000 plus years before we actually had the ability to derive them? Yeah, it's obvious. It's the same place Velcro comes from, I would say. Aliens. I mean, come on, pyramids, Chichen Itza. I told you guys about that 3,000-year-old Mayan ruins where they had perfect geometry, and it's like, yeah, it sometimes it's unfathomable. Try to fathom that, right? And you go, how do they know this? I don't know. I actually have no idea how they could have even had a notion about things like that, because it took a few thousand years before we could prove it. I would like the circumference, but not because you memorized it. No, I need you to show me, because I've never seen this. I've never heard it, and I might not believe you if you just give me a formula. So how do I do this? I start by parameterizing the circle. Now notice I centered it at the origin to make the algebra a little bit less scary. So what parameterization do you want to use? Yep, let's do the same thing we did before. And then r sine t. So, dx dt. I think we've done this one a couple times today. dy dt. Remember, r is a constant. And by the way, this is a whole circle. What boundaries should I use for t? Is 0 to 2 pi the only thing I can do? It's probably the safest. Really, any interval that is 2 pi long. You could go negative pi to pi. Saying I want to go from 6 pi to 8 pi doesn't really make a lot of sense, does it? I mean, 0 to 2 pi is the most logical, but it's basically any interval that is 2 pi long. But that's the safest one, because I don't know if choosing a different interval might change my answer. So clearly we want to say this. Now, those will end up being my limits of integration, won't they? Now, are we making any assumptions about a circle? No, but we've proved the Pythagorean identities. We prove cos squared plus sine squared equals 1. I do that on day 1, first 20 minutes of Calc 1. I prove it. It's a really simple Pythagorean theorem. And I can prove the Pythagorean theorem too if you want to stay after class. That's just simple geometry. I taught geometry for years in high school. Those we're not questioning. I'm not using any properties of circles to do this. But I do know that sine and cosine will work. So now, my arc length is from 0 to 2 pi of what? Well, this squared plus this squared dt. Do you agree with that? R is the radius. R is a constant, but R is non-negative. R is not going to be 0, but So what do we have here? We have r squared sine squared t plus r squared cos squared t. And if I factor out the r squared, now I have r squared times sine squared t plus cos squared t, all dt. So what does all of that reduce to? Just r, because sine squared plus cos squared is 1, and I have the square root of r squared, which is just r. Oh, all right, so now this is 0 to 2 pi of the constant r. It's 0 to 2 pi of the constant, so my answer is just 2 pi times r. Why? Because you're integrating a constant. Well, that's kind of convenient, because isn't that what we know the answer is? But this is the proof. You can't accept it blindly, but there's a proof. Now, you got to admit, that's kind of cool. We just used our arc length to figure this out. There is a tricky one that I'm not going to do in this class. We actually do this on the third to last day of Calc 3, because we can't do it until then. The arc length of an ellipse. Turns out that's really gnarly if I'm trying to do it using calculate methods. Why? Because in the ellipse, remember, I have different coefficients on the x and y. So when I do the parametrization, see, this worked because I could factor the r squared out of there. But if I had different coefficients on the sines and cosines, I can't factor a number out of there. So, and you also won't get a sine squared plus cos squared sitting by itself. So the ellipse is actually really, really challenging if I was trying to do it this way. There is another way that we're going to learn late in Calc 3 that has nothing to do with the geometry. It's a powerful Calc 3 formula, but then I can apply it to finding the arc length of an ellipse. It's really cool. And when you get the answer, you go, you know, that's the reaction everybody has. Okay. Any question on this? We're good? All right. Let's do more. It's not about the answer, it's about the setup. Is there a guarantee you're going to be able to integrate anything that is thrown at you here? No. No. So it's not about, I'm going to grab a problem out of a textbook here. I'm not that good at making up things like this. Oops. Hold on. 13. There you go. Let's find, here's one. Let's say that x equals 5t squared, y equals 2t cubed, and t is going to go from just 0 to 1. Fairly short. Okay? At the very least, I'd like to set up the problem. Now, if this were Calc 1, I'd need to write y in terms of x or x in terms of y, which we could do, because you could solve for this t having a cube root of y, substitute it in here, and it's kind of icky, but you could all do it. That's, you know, it's not beyond what we could handle. Okay? So let's do this one. So dx dt is 10t, dy dt is 6t squared. So what I actually like to do next is I don't like to go right to the integral. I don't like writing integral equals integral equals integral while I'm doing all my simplifications. So what I usually will do is I'll do this first. I didn't in that problem, but I'll usually go like this. I'm going to do all my prelim stuff first. All right, so what is this? So it's what, 100 t squared?
Plus 36 t to the 4th.
Now, all of that is going to go under a square root in a moment, isn't it?
Yeah.
So it might be a good idea for us to factor out something if we can. Is there anything common?
2t squared.
I can keep going. A little more.
4t.
How about 4t squared? And what would that leave you with?
25 plus 9t squared.
Plus 9t squared. Okay, good. So now the square root of 4t squared, 25 plus 9t squared is what? Well, it'd be 25 plus 9t squared
Times
2t. Do I have to worry about square root plus or minus? No, t is between 0 and 1. Okay, we've just done all of our prelim stuff. So can you now tell me the arc length of this curve? S is going to equal the integral from 0 to 1 of this. How about if I write that as 25 plus 9t squared to the 1/2? times 2t dt. Do I need a trig sub? No. What do I need?
U sub.
Just a simple U sub. Ooh. That's why we factored it out. If we hadn't factored it out, we'd be staring at it going, I don't know what to do. So, what do you want to do? You want to let U be what?
9t squared plus 25.
The whole thing.
Yeah, 19.
25 plus 9t squared, then your du is going to be
18t.
18t dt, and I have a multiple of that. Okay? So I can either change the limits, or I can just integrate this. It won't make any difference. But what do I need? So sometimes we forget. So here's what I do. Avoid any errors. What needs to go here?
18.
That's the safest way to not mess up your coefficient. Do I now have u to the 1/2 du? Is that correct?
Yes.
Oh, they're saying half.
No.
What is the antiderivative of u to the 1/2 du? I'll write it to the side.
1/2, or no?
We'll do the exponent first.
2, 3 thirds. 3 over 2. 2 thirds.
Yes? No? Maybe?
Yes.
I just wrote u to the 3/2 times 2/3. Because if you want to change the variable, that's fine, but you have to change the limits, and under no condition that exists do you ever change back. That's the one thing that drives me crazy as a calculus person, is that people will change the variable in a definite integral and somehow change back. You can't change back. There's nothing to change back to. You have a numerical value. So what ends up happening is we write 2 or 3 different numerical values for our answer. Usually none of them are right. Now, can that be cleaned up at all?
Yeah.
A little bit. What's this going to be?
2 over 27.
2 over 27. Now, I need to evaluate at both ends, by the way. So at 1, what do I have?
That's 25.
34,
34 to the 32.
which everybody knows off the top of their head, right?
No.
Okay. And then minus
25 to the
25 to the 3/2. That's actually a nice number. Square root cubed would be
125.
125.
Yeah.
Now what? Wave at it, if you walk away. I don't think you're going to get any better than that. 34 to the 3/2 cannot be simplified, and distributing the 2/27 is correct, but just kind of ugly. Now, if I really need a numerical value, I'll just put that on my calculator, right? Now, what is something you probably should check really quickly?
If you-
Is this
Is this positive?
positive? Ooh, what if that's negative?
You did it wrong.
Then I've got a huge error. Do you all know 32 to the 3/2 off the top of your head? I mean, you probably should by now, right? No, so why don't we check? Is it possible we have an arithmetic error anywhere along the way? Yeah, but it'd really be the last step. Let's check that really quickly. 34 raised to the 3/2 minus 125 is approximately 73 point something. That's a good thing. But what if it had been negative? That'd be a bad thing. More likely the negative is not because you evaluated badly. The negative is more likely because you just switched the order of subtraction. Does that, even at this level, do we sometimes do that? Yeah, actually, even at this level, we sometimes make that error. We switch the order of subtraction inadvertently, and now we've reported a negative Arclength. That can't happen. Can you even have a 0 Arclength? No, because you started and stopped at a different place. You can't have 0. Well, what if I come back to the beginning? Well, definitely not 0, right? That'd be like saying a circle has 0 circumference. Yeah, starting and ending at the same place, actually, that means you have a closed shape. Often, it ends up being simpler, depending on the shape, of course. Okay, we cool so far? All right, let's try another one. I'll start with this. Okay. Oh, I have a great one. Essentially, I want the length of the curve in the first quadrant of my ninja's throwing star. So if I asked you for the entire arc length of the ninja throwing star, what can I do with this answer? Think about it logically. A ninja throwing star, right, looks like this, and I just asked you to find this piece here. So if I wanted the whole thing, what would you do with your final answer? Multiply by 4, yeah. The problem is you can't do the whole thing at one time for multiple reasons. I'll give you a hint though. If I said, well, why don't I just do my integral from 0 to 2 pi? I'll tell you what you're going to get. You're going to get 0. You're going to get 0 because this isn't a function in XY world. I can't do that thing from, it won't work. So instead I'm going to go 0 to pi over 2. Because we know from symmetry that would be good enough. Now, for all practical purposes, if I do want the whole thing, I can show you how to manipulate it, but we would run into some difficulties if I try to do this as one integral. It really can't be done. That's why we didn't do the circle in XY world as one. If, by the way, the circle is 1, using the Calc 1 arc length formula, 1 plus the square of the derivative under the square root, if I do the top half of a circle, I will get exactly half the circumference. And then I just simply double that for the whole circle. You can't do the whole circle as one integral because it's 2 different functions. That's why you couldn't use it in Calc 1 to do the whole thing. But you could do half the circle. So in this case here, I don't need to rewrite this. I'm just going to differentiate as is. And we've already done this today. So dx dt is what? -3 cos squared t sine t. dy dt is +3 sine squared t cos t. Often, when you're doing problems of this nature, you're often asked for things like, tell me the first derivative, tell me the second derivative, tell me the arc length. All at the same time, because you're using the same terms. You're using those derivatives for every part of this, so why not ask multiple questions? So if I asked you for dy dx, you're going to give me the quotient. I'm asking you for the arc length. Okay, so you're going to take the sum of the squares, but you still had to do this. So the next thing I'm going to do, I'm not going to write the integral until I get done with the algebra. It's a little cleaner this way. So when I square each of these, what will I get? Okay, obviously I can factor something out of this. Agreed? What's common?
9
I'll do my part.
cosine squared sine squared.
And what does that leave behind?
Cosine squared plus sine squared.
Oh, you like that?
Yes.
I like that.
It's triggered in.
That's just 1.
Yeah.
So this is just
9 cosine squared
this.
sine squared.
Now, where's all this going? It's going under a root. Is that quantity under the root a perfect square? Yes, it is. Can I take advantage of that? Well, if I don't, good luck integrating that. Right? But it is a perfect square. Now, do I have to worry about plus or minuses? Normally I would, but where do I live? In the first quadrant only. This is one of the reasons why you can't do more than the first quadrant. If I just said 0 to pi, for example, we have a problem. Because isn't that negative half the time?
Yeah.
Oh, that's why I would have a problem if I did anything more than the first quadrant. So I'm keeping it simple for you in that sense. So what will this be since I am in the first quadrant? This will be just
3 cosine sine.
okay. Finally, I can claim that the arc length is the integral from 0 to pi over 2 of 3 cos t sine t dt. All right? Can we integrate this one?
Yeah.
Does it matter which one I choose as my u? We've done this before. Remember, this is the row your boat problem. But if you want to avoid negatives, which one do you probably want to choose? U being probably sine, because then your du is positive cosine. So this is of the form u to the first du. Agreed?
Yeah.
What's the antiderivative of u to the first? 1/2 u squared. That's all you gotta do. And, sorry, there's a 3 there, sorry. 3 halves. Almost lost my 3 there. And what is this? Well, sine of pi over 2 is 1, sine of 0 is 0, so my answer is? Okay, look at my functions. Look at the interval that we integrated over. And my answer was 3 halves. Does that seem odd? My answer is a rational number. I have pretty irrational looking functions, right? And even if I did it in XY rule, they'd be things to the 2/3 power. And we got 3 halves. I know, I find that kind of interesting, that we got a rational number for everything in the problem being irrational. Irrational everything's. Is that a head scratcher a little bit? Maybe. We've seen this movie before, though. I'm going to show you something that you did probably the first day of integration. Well, one hump of a sine wave. Well, let's see. I'm going from 0 to pi. Almost every single calculation gives me an irrational height. Right? Pi over 2 is the exception, right? Everything's an irrational height. I have an irrational length interval. So obviously I'm going to get some crazy, horrific, terrible answer. Agreed? So we did sine x dx from 0 to pi. That gave us negative cos x from 0 to pi, which was the negative of -1 minus 1, which was 2. One hump of the sine wave had area exactly 2. Irrational limits of integration, irrational every coordinate on the whole thing. Other than pi over 2 comma 1, there are no rational numbers that I'm even going to see for the most part. Right? Everything's got at least one irrational number, yet the area was an integer. Go figure. Does that make sense? I'd like the length of that.
Why?
Can we find the length of that curve? In Calc 1, by the way, there's nothing to parameterize because it's already a sine. If we were doing this in Calc 1, I want to find the length of this curve. Is it a semicircle? We know this for a couple of reasons. A semicircle would have vertical tangents, first of all, wouldn't it? And that slope is 1 and that slope is -1. Secondly, this is 0 to pi, but this is 0 to 1. So is it elliptical?
Yeah. Or half of it, I'm saying.
But again, same problem, isn't it? That it's more like a lemon drop. Is that an accurate description? In other words, that's a point. That's sharp. So this isn't a semicircle on top. This isn't a half of an ellipse on top. There's no trick. If I wanted to find the arc length of this one, I would use Calc 1 techniques because there's no parameterization. It's already the sine function. What would I parameterize it as? And so what we would do is say, well, what's dy dx? That would be cos x. So 1 plus the square of dy dx is 1 plus the square of the cosine function. So I can say with absolute certainty that the arc length of this is this. That is the answer. And then what would we do? Again, we wave at it as we walk away. But can't I use some trig identity? It's 1 plus cos squared. No, so we're kind of dead in the water there. Now, is it possible there may exist some really crazy, weird trick? Yeah, I don't know of any. This is Calc 1. Most of the problems that exist in Calc 1, you stated this. Now, what if I really need a numerical value? Well, then you use a computer. And what's the computer doing? It's literally doing Riemann sums with incredibly short iterations. That's how it's giving you decimal accuracy. You can't do that by hand. It would take you forever. What do I mean by short iterations? Imagine I did literally 1 million little line segments and found the length of each of them and added them up. Probably be ridiculously accurate, wouldn't it? It might take me, a couple hours. Or a couple months, I don't know. It would be beyond what I would want to do by hand. That's where the technology would come in. I could give you a decimal approximation, but I'm not going to be able to give you an antiderivative. What we're looking at specifically are problems where we can actually integrate them. So I don't really want to spend time on the problems that we can't integrate. That's what Calc 1 was. Again, I have a book right here, and this is the Swikowski. So when I go to that, I'll go to that specific section of material. So what is it? Arclength. And it says, read that out loud for me.
Set up integral for finding the arc length.
That's every question in the book. Did you hear what he said? The instructions are, set up the integral to find the arc length. Why? Because you can't find the arc length, you can tell me the integral. Knowing there may be more techniques down the road. There's a handful of things you could do now that you couldn't do in Calc 1 because you know things like partial fractions decomposition, trig sub, integration by parts. It doesn't add a lot, it adds a few. But now that you also know the parametric version, it actually adds quite a bit more. And then next semester, we're going to actually be able to do a lot of problems. When we go to 3D, it actually opens up more doors, strangely enough. Okay? Let's see. Question was material for exam. This is the end of the material for the next exam. So let's go ahead and stop that.